All right, today we are pulling back the curtain on how pretty much all modern software is actually built. We're going to dive into the fundamental building blocks that make everything, from the apps on your phone to the operating system on your laptop, even possible. Let's jump right in. Have you ever stopped to think about that? I mean, your phone just knows that a contact has a name and a phone number, or that a photo has a location and a date. How in the world does it keep all of that straight? Well, by the end of this, you're going to understand the really elegant concept that makes it all work. So the secret sauce here is something called an object. The easiest way to think about an object is as a little digital stand-in for a real-world thing or idea. See, programmers create these objects to kind of mirror reality inside the computer. And every single object has two key things: its state, which is just the information it's holding, and its behaviors, which are the actions it can perform. Okay, let's make this real. Imagine we're coding a super simple game with a bouncing ball. That ball would be an object. Its state, the data it needs to remember, is its current height off the ground. And its behavior? What can it do? Well, it can report that height to another part of the program. Simple, right? The state is what it is, and the behavior is what it does. Let's try another one. Think about a cashier line at a grocery store. If we wanted to build that in software, the line itself would be an object. Its state would be the number of customers currently waiting. And a key behavior of any line, well, you've got to be able to add a new customer. And get this, when you perform that add a customer action on the line object, its internal state actually changes. So now we know software is basically built from all these little digital objects, and each one has its own data and its own special skills. But that leads to the next big question, right? If your program needs, say, 1,000 bouncing balls or dozens of different cashier lines, do you have to build every single one from scratch? Where do all these objects actually come from? They come from a class. And here's the trick. A class isn't the object itself. It's the master blueprint. It's the template, the cookie cutter, the set of instructions that defines what all objects of a certain type are going to look like and how they're going to act. It's the recipe you use to make the actual objects. And you know what? This blueprint analogy is absolutely spot on. Think about it. A physical blueprint for a house specifies the materials and dimensions. Well, a software class specifies the object's internal state, its data. The house blueprint defines features, like doors and windows. The class defines the object's behaviors, what it can actually do. It is the exact same concept, just applied to code. So let's bring this back to our cashier line example. You wouldn't code each line one by one, no way. Instead, you'd design a single class, that master blueprint, and maybe you'd call it Q. This Q class would lay out all the rules for how any line should behave. It has to keep track of the number of customers, and it has to have a way to add a new one. And this is where the magic happens. Once we have that one Q blueprint, we can use it to stamp out as many individual line objects as we need. We can create line A for the first cashier, line B for the second, line C for the third, and on and on. They all follow the exact same rules from the Q class, but each one is a completely separate, independent object with its own state. So here's the crucial point. Each one of those objects, line A, line B, is called an instance of the Q class. It's just like building 10 houses from the same exact blueprint. You end up with 10 separate real-world buildings, right? Same deal here. 10 line objects created from the one Q class are 10 separate, unique instances living in the software's memory. And these instances, they really do have a life of their own. It all starts with creation, where they're brought into existence, usually with a keyword like new. Then comes manipulation. For their whole lifespan, they're getting messages sent to them that change them or ask them for information. And finally, there's destruction. When the program is done with an object, a process called garbage collection comes along and automatically cleans it up to free up memory. Pretty neat. Now, the real power here isn't just about making objects. It's about how they all work together. A complex program is like this bustling ecosystem of objects, all communicating and interacting with each other by sending messages back and forth to get the job done. So what does sending a message actually look like? Well, it's a pretty simple three-step dance. First, our line A object exists, and it has its own internal state. Let's say it has 5 customers. Next, another part of the program sends it the add customer message. Finally, the object gets that message, does its thing, and its state changes. Now it has 6 customers. It's a simple cause and effect. And this really gets to the core of what's called object-oriented programming, or OOP. It's all based on this idea of sending messages to objects. Those messages can either change the object's internal data, like adding a customer, or they can just ask the object to return some of its data, like asking our bouncing ball, hey, what's your current height? Which brings us to the big so what question. Why go through all this trouble with blueprints and instances and messages? What makes this model so powerful that it's the foundation for basically all modern software development? Well, there are three huge, game-changing advantages. First, it manages complexity. You can take a massive, terrifyingly huge problem and break it down into smaller, self-contained, understandable objects. Second, code reusability. You write one good blueprint, one class, and you can reuse it 1,000 times without rewriting anything. And finally, and this is a big one, it lets programmers design software that actually mirrors the real world, which makes the code way more logical, intuitive, and easier for other people to understand. So the next time you use an app on your phone, just remember that silent architecture running underneath it all. Countless little objects, all stamped out from these elegant class blueprints, all talking to each other to make things happen. It kind of makes you wonder, if classes are the blueprints for the digital world we live in today, what are the essential blueprints we're going to need to design for the world of tomorrow? Something to think about.